Okay, this is the main topic that we're on to now. So last time we ended up spending most of the time talking about things about locally convex spaces, measurability, integrability, and so on. So today we'll see how that applies to vector fields. But before we get to that, in order to sort of be able to state everything, the results all together kind of in a lump, one of the things we'll do is talk about a different kind of topology for spaces of vector fields. And this is very much related to when we talked about mappings, we had the weak PB topology. And so the idea with the weak PB topology is that you use functions to describe the topology rather than the mappings themselves. So you use the fact that mappings act on functions by pullback to give you a topology there. And you do the same thing here for vector fields, but now the vector fields act on functions by Lie differentiation. Okay, so so we're going to talk about what I will call the weak L topology. And so this is straightforward to describe. All right, so we'll do we have the usual thing. Okay, so we'll talk about manifolds of class CR, smooth, real analytic, or holomorphic, and mappings, or vector fields in this case, of that regularity. Okay, and I'm interested now in this space of vector fields. Okay, so vector fields of class C nu. Okay, and so given an f, which is a CR function. Okay, you have a mapping like this. L sub f. I'll write it. Okay, so L sub f is a map from the space of vector fields of class C nu into the space of functions of class C nu, and it simply maps the vector field x to the Lie derivative of f with respect to x. Okay. All right, and so so you know what's coming now. You have this family of mappings. And so we're going to regard this guy as a locally convex space. Okay, the space of C nu functions on M. We'll regard this guy as just a vector space. Okay, and so for this family of mappings LF, where F runs over all CR functions, you have this mapping, and so therefore you get an initial topology here, which is the coarsest topology for which all of these mappings are continuous. Okay, so this is the weak L topology. For the space of C nu vector fields. So it's the initial topology. With respect to all these mappings. Okay. All right, and so in all cases, right, of nu, okay, and the only requirement here that I will have is that in the case of holomorphic vector fields, I need to have the M is Stein. Okay. This topology agrees with the other topology that we had for the space of C nu vector fields. Okay, so we had previously defined a locally convex topology on here, and what I did was explicitly gave you the semi-norms for that locally convex topology. Okay.
Sorry, so
Yeah.
in that case, that's again the global holomorphic coordinate?
Yeah, so you need to have around every point in M, you need to have a coordinate chart whose coordinate functions are globally defined holomorphic functions. Yeah.
And how can you get away with this in the real analytic case?
In the real analytic case, that's true, because of Grauer's embedding theorem.
Okay.
Yeah. So in fact, I mean, what I will do here is I'm not, the proof of this in most of these cases is just kind of messy estimates, right? You have to prove equivalence of sort of two locally convex topologies. So you have two different kinds of semi-norms, okay? So the fact is, what are the semi-norms for the weak L topology? Okay, so maybe I'll write that down. Okay, and then because it's, there's lots of interesting things going on here, and this is a good place to illustrate one of those things. And that is when you have initial topologies, like we have here, and you have semi-norms here, it naturally induces the semi-norms for the initial topology here. So I'll tell you what those are. So the semi-norms for the weak L topology are, okay, so they're the semi-norms which map a vector field to right? So I'm using this abbreviated notation that I talked about before. Okay. So remember that the semi-norms that we used here, I wrote those down explicitly. I'm not going to go through all the various cases again. But I wrote down explicitly the semi-norms here, and they all depended on a compact set K, so that's the K there, and then some other data. Okay, so for example, in the smooth case, the data, extra piece of data was the degree of differentiability, so you had these indexed also by an integer m. And for the real analytic case, there was this sequence of positive numbers converging to 0, so there was dependence of the semi-norms on that. Okay, so that's kind of embedded in the pk nu notation. Okay, and so the semi-norms for this topology are these, where k runs over all compact sets. F runs over all CR functions, and then there's the other data that indexes the semi-norms, depending on what nu is, okay? So you have these explicit semi-norms, and so essentially what you're doing to prove the equivalence of these topologies in most of these cases is you're proving that the equivalence of two topologies defined each by explicit semi-norms, right? So it's messy estimates. However, one of the things that I'll do, because I think it is helpful to clarify what's going on in the analytic case a little bit, is I'll write down one interesting little fact and an interesting proof of that fact that you have to do to prove this in the real analytic case. So what I'll give you is the only part of this argument that's nice, basically. All of the other things are messy estimates. There's one thing you can do that's really very elegant and beautiful, and that's, so to prove that the weak L topology for the real analytic vector fields is a subset of the normal topology okay. It suffices to show that you have, okay, so you have a set of real analytic vector fields like this, and then for each real analytic function f, you have this mapping LF, okay? So this goes to the real analytic functions, okay? And to show this inclusion, if you think about it for a second, it suffices to show that this mapping is continuous for the normal topology here. So what I will prove for you is the continuity of this mapping, because I think it gives you some insight into how to use the various definitions we had for the real analytic topology. So what I will do is I'll just sort of sketch this diagrammatically, because it's really just a diagram.
And is it a dual relationship or just?
Say it again.
Is it a duality here, or just weak is used for the sake of weak?
Oh, is there a strong? Oh, no. That's right. No, it just doesn't. It means weak in the sense that it's defined through mappings, just like the weak topology is for the dual, right? You have mappings, right?
So is it then LF is the dual space of the set of?
No. It's just you have mappings. That's where the similarity ends, right? You know, you define say the weak star topology or the weak topology by evaluating on either elements of the vector space or the dual. So it's an evaluation process that gives you the topology. Here it's an evaluation on F.
I see.
Yeah, that's how you should think about it. Okay. Okay. Yeah.
So here, I guess the way you prove this is maybe again to go local coordinates. And basically, you would use F to be the coordinate functions, right?
In one direction, you use. That's right. Exactly. Yes. That's why you need the global coordinate functions. Exactly. So all of these things really boil down the way you do all of them, except for this one, right? But this one's. I'll give you the slick version of this one. But a lot of these, and even this one uses the holomorphic version. I assume the holomorphic version is already known, right? So in the holomorphic version, you do that. So even here, that's in the background. Yeah. Okay. Okay. So what do you have to do? So we're going to use actually both descriptions of the real analytic topology, and so remember that you have the set of real analytic vector fields, and what you have here. So we had this set NM. So this was the set of neighborhoods in some complexification M bar of M. Okay, so we had neighborhoods of complex neighborhoods of the real analytic manifold in its complexification. That we denoted by that. So for every U bar in here, we had a restriction mapping. Okay, so we have gamma holomorphic R. Okay, T U bar. Sorry, I'm going to need more space there. Just a moment. Okay, so we had gamma holomorphic R T U bar. Okay, so we have a mapping like this. Okay, so what's that mapping? That mapping is the mapping which says you have a holomorphic vector field. So these are the holomorphic vector fields on this holomorphic manifold U bar, open subset of M bar, okay, that when you restrict them to M are real vector fields, okay? So we had a mapping like this, and this was literally just restriction. You just evaluate on M, okay? So I had this restriction mapping, which I'll call R, U bar, M, restriction from U bar to M. Okay, and then I told you that one of the characterizations of the topology here was that it was the final topology, so the the finest topology for which all of these mappings are continuous. Okay, and now, given that that's the final topology here, to show that this mapping is continuous, what you have to show is you have to show that that mapping is continuous. That's necessary and sufficient to show continuity of this guy. Okay, so you have an induced mapping here. So what we're going to show is the continuity of this one. Okay, so how are we going to do that? Well, now we're going to use the other description of the real analytic topology, which is that you take a compact set K and you surround K. So then you had okay, so here M was contained in U, and here K is contained in U. Okay, so these are the neighborhoods of a compact set K of M in this complexification M bar. So we had mappings like this. Okay, so this was these are germs. Yeah, like that. Okay, yeah, and Okay, so these are germs of holomorphic functions around the compact subset K, and we had mappings like this. Okay, so what's the mapping here? The mapping here goes like this. Take a real analytic function. It can be extended in some neighborhood of K to a real analytic function, and take the germ of that real analytic function. That's that mapping. Okay. So what you have to show then, if this mapping is going to be continuous, then this mapping has to be continuous. Okay. For every f. All right, that's the initial topology description here. All right, so then, so what we have to prove then is we have to prove that this mapping is continuous, and I'll call this one inclusion. This is kind of an inclusion mapping, IK bar. Okay, so you have to prove that. So it's R U bar M composed with LF composed with I K F R. You have to show continuity of that. Okay. All right, so how do we do that? Well, as I said when I answered Abdulraz's question a second ago, we're going to use the holomorphic result. Okay, so what we're going to do is we're going to choose. Okay, so this is the part where you have to know something about real analytic geometry, and so what you know is that in this set here. Okay, so this is a directed set of neighborhoods of M in M bar. In this directed set are neighborhoods that are Stein. Okay, so they're open subsets, neighborhoods of M that are also Stein manifolds. Okay, now Grauert in his paper where he proves the embedding theorem, what he proves actually is that in here, okay, you have this other directed set of Stein neighborhoods of M. Okay, so this is the subset of neighborhoods that are Stein. Okay, and so what Grauert proves in categorical language is that this is cofinal in here. Okay, so what that means is that given every U bar in here, you can find a Stein neighborhood contained in U bar. All right, so that's one of the things that Grauert proves. So we're going to choose a Stein neighborhood which is contained in U bar. So this is going to be so I'll squeeze it in here. Okay, so I have this Stein neighborhood, which I'll call S bar.
So the cofinality has to do with the reverse inclusion direction, right?
I don't know if that's, my dyslexia makes me unable to answer the question in that form. So what it means is exactly what I said. So given a neighborhood here, there will be one that's smaller in Stein. And if that's what you meant to say, then yeah, sorry. I get mixed up with these reverse inclusion things. Yeah. Okay. But yeah, it has to do with the way the set's indexed. So I guess that's maybe what you meant, right? Yeah. Okay. Okay. So now you have a mapping here. Okay. This is the restriction mapping from U bar to S bar. Okay. So that's just restriction. Then you also have the restriction mapping going here, which is R S bar M. Okay. And obviously, this restriction is the composition of these two. Okay. All right. Oh, and then you have, okay, so given an F, okay, you can find a Stein neighborhood S bar so that the function F extends to a holomorphic function F bar on S bar, and then you have this mapping L F bar, which goes to C hol R of S bar. Okay? Does that make sense? With more space, I would have made that diagram more square. All right? Okay, so now, what you know, so I'm assuming we've already done the holomorphic case. So in the holomorphic case, I know that this mapping here is continuous. Okay, that's one of the things that you prove when you do the holomorphic case, is that this map is continuous for every F bar. Okay, so all we do now is we basically just rewrite this, okay? So this is then I, K, M bar, and so let me, okay, and so what's the mapping here? The mapping here is just, and I'll write this as, let's say I, S bar. Oh no, sorry, this is again R, S bar, M. So I'm using R, S bar, M for two restrictions. One to the space of vector fields, one to the space of functions, okay? So I go, okay, so LF, okay, so LF, here, let me do it this way, so I can try to get this right. All right, so I have this mapping that goes from here to here. Okay, so what I'm gonna do is I'm gonna go over to here, down to here, and across there. Okay, so that's going to be, all right, so it's going to be R, U bar, S bar, okay, then L, F bar, okay, then R, M, what is it, S bar, M, like that, okay? Did I do that right? Okay, all right. So these two things agree, okay, but so you have to show that that diagram commutes, and it does. All right, now you're done, right? Because everything here is continuous. This is continuous, restriction mappings are continuous, that's easy to show. This is continuous because we're assuming that the result holds for Stein manifolds. This is a restriction mapping, so it's continuous, and this is continuous by the definition of the real analytic topology on the set of real analytic functions. Okay?
So you've transported your evaluation to the holomorphic thing.
Exactly. Yeah. Okay. All right, so that's a nice sort of illustration of how you can of how you use holomorphic things to prove analytic things.
So in the same vein, so as a slide kind of a crazy idea. So you have a big tool there in the real analytic case, which is grounds, right?
Yeah.
Which you don't have in the holomorphic case. So you need Stein to have these global coordinates.
That's right, yes.
Can you, when you start with this holomorphic manifold, can you...
Not necessarily Stein.
Not necessarily Stein.
Yeah.
Can you look at it so as its realification, kind of the real analytic underlying manifold?
So of the same, of twice, whose real dimension is twice, yeah.
And then apply ground to that.
Yeah.
You know, so you can...
So are you asking if this result holds in the non-Stein case? This result is false in the non-Stein case. Yeah. And it's easy to see why. Let me give you an example of why. Take the Riemann sphere. Okay. The only holomorphic functions on the Riemann sphere are constant, right? So when you differentiate those, you get 0. There's no, so in other words, all those maps LF are 0, right? So you can't do anything with that. Yeah. So you really need to, I suppose it's possible there may be some non-Stein manifolds for which this is true. I would guess not. Okay. But certainly there are non-Stein manifolds for which it's just false.
But can you do without holomorphicity and just evaluate with meromorphic functions?
Oh, I don't know. Yeah, that I don't know.
Because with meromorphic functions, you have still analyticity outside of the system.
Yeah. So really the issue here is going to be to what extent a manifold can be described by, the actual analytic structure of the manifold can be described by its meromorphic functions. I don't know what that is.
Because again, they're much richer classes, of course.
Yeah, absolutely. Whether they're rich enough, I just don't know. I've never seen any results like that, for sure, but that doesn't mean anything.
It's just a huge class.
Exactly. That's right, and the problem with holomorphic is they're small. But the issue here really is that, these things are global, right? So I'd be a little bit surprised if they're rich enough. Yeah, because these are globally defined meromorphic functions. Yeah, and so, but I don't know the answer actually. Yeah. But yeah, that's the key issue is the existence of enough CR functions to do what you need. Yeah. Okay, good. So this is the weak L description of the topology. All right, so now finally we can talk about time-varying vector fields. Okay. Okay, so because I want to, we're going to be using the WeCal description of topologies, so we're really going to be talking both about functions and vector fields. The initial part of the development will be not for time-varying vector fields, but for time-varying sections of a vector bundle. Okay, so I let this is an R vector bundle. Okay, so what I want to describe are time-varying sections of this vector bundle. So I'm going to let, that's a blackboard bold T, like that's a blackboard bold R. Okay, so I take T will always be an interval. Okay, all right. I'm sorry. Okay, so I'm going to write a time-varying section as C, right? So it's a function of time and M. And dissectionness, of course, means that C of T x is in E sub x for every x. Okay, so I have that shorthand, that's an x. Okay, so you can freeze one of the arguments and consider it as a function of the other. Okay, so a C nu, okay, so I still have a nu here, and this is going to hold for all nus. Okay, so a C nu Caratheodory section okay. So it's a mapping again C from T cross M into E. Of course, it satisfies the section condition, so I'm not going to reproduce that. Such that, okay, C sub x is measurable for each x. Okay, so you freeze an x. Okay, then this mapping, C sub x is a function of t, and it takes its values, of course, in the fiber, E sub x. Okay, and so the fiber E sub x here is a finite dimensional vector space, right? So there's no ambiguity about what measurable means there. Okay, so the finite dimensional vector space will have its standard Euclidean topology. All right, and CT is class C nu for every T in there. Okay, so that's Caratheodory sections. Okay. So let's characterize these. We're also going to talk about integrable and bounded sections, but let's first of all classify the measurable guys. so there's a list of equivalent statements. All right. Okay. Well, actually, so here, just because I'm talking about sections, I only have two. For vector fields, we have two more, so I'll add those on. So here, it's that the mapping T goes to CT. CT. All right, so this takes the time and gives you a C nu section, C sub T. Okay, so this mapping is measurable. Okay, so this was the measurability that we talked about last time. And just to clarify, I had this confusion between open sets and Borel sets last time, so I really meant Borel sets. Preimages of Borel sets are Lebesgue measurable. That's the definition of measurable. Yeah. Okay. All right. Okay, so if E is Tm, then we also have, okay, you have the weak L versions of this. Okay. And that is so L F L X F is a C nu Carthay-Dory section for every CR function F. Okay.
You mean C, right?
No, we're talking about vector fields now.
Okay.
Yeah, so X is exceed. X is exceed. Okay, and also L X, so T maps to L X T F. Okay, so this now will take its values in the space of C nu functions. Okay, this is measurable. Okay, all right. So how do you prove this? So there's some. So basically, the proof for all news is the same, and what it amounts to is that you have these evaluation maps. Okay, so for X in M, you have the mapping evaluation map at X. So what's this going to do? This is going to map your C nu section, okay, into this finite dimensional vector space, E sub X, okay, and of course it's just C sub T of X. Sorry, just there's no time varyingness here. Okay, so I have these evaluation maps. Okay, so this definition is saying that the composition of this mapping, okay, from time into the space of sections into E sub X, it's the definition of a Carthay-Dory section is that that mapping is measurable for every X. Okay, so really then what you're thinking about is you're thinking about the properties of these evaluation mappings. Okay, so these evaluation maps are point separating. Okay, and so what you then use is you use this theorem about measurability of mappings taking values in Suslin locally convex spaces, and that is to test measurability. It's sufficient to check their measurability on these evaluation mappings. Okay, so the equivalence here is really just about Suslin spaces.
Sorry, one question. The
Yeah.
fact that you insist that the free measure of Borel be Lebesgue measurable,
Mhm.
is it because you're going to do some modifications on a subset of measure zero, this kind of thing? Or?
Oh, as opposed to Borel measurable?
Exactly. Because that's what
I mean, there's nothing deep there. We just decide we're going to use Lebesgue integral as the measure, not, the Lebesgue integral restricted to Borel sets.
I see.
Yeah, I mean, there's nothing deep there. Remember, it was about a measure space before, right? And, so you're talking about two different measure spaces. Yeah, but it just has to be a measure space. Yeah.
But could you have done the same with Borel?
Yeah, it's a measure space, right? It's not complete.
It's not complete.
Yeah, and I don't recall completeness being needed anywhere here. Yeah, but I have to say, I could be wrong. Yeah, but I don't recall completeness being required for this result. Do you remember, Rob?
No, I don't.
Yeah, I don't. But it is possible, but I don't think so. Okay. Okay. And then the similar sort of thing happens here. Okay. To prove, say, equivalence of 1 and 2. Okay, so what you have here is you have these kind of evaluation mappings. They're kind of evaluation mappings. That's kind of the answer to your question about weak and strong before, right? You have these kind of evaluation mappings, LF. So these are evaluating a vector field now on a function, but it doesn't give you, well, not quite a number, but here it gave you an element in a finite dimensional vector space. Here it's giving you an element in another infinite dimensional vector space, but it's still some sort of evaluation mapping. But that was exactly the situation that we talked about before, because remember that we had these, we had these two Suslin spaces and a mapping between them, which came from some subset A of mappings. Okay, so we're using here the Suslin property to establish the measure, but the equivalence of 1 and 3 as well. Okay, so those are so I mentioned when we talked about this last week that the Suslin property is used in two places, and you can see it here: the equivalence of 1 and 2, and the equivalence of 1 and 3. Okay. All right. So now let's talk about integrability. Okay. All right, so basically, integrable sections, you kind of, the definition is going to go case by case a little bit, using semi-norms. All right, so for integrable and bounded Caratheodory sections, okay, so when I say integrable here, you should be thinking L1, and when I say bounded, you should be thinking L infinity. Okay, I'll make this clear in the definitions in a second. Okay, so we give definitions. Case by case. All right, so. And they all kind of look the same, but it gives you a very concrete description in terms of semi-norms. Okay, so first we'll take nu equals m, so finitely differentiable. Okay, so here's how the statement goes. It says for every compact. Oh, sorry. I should set this up so you know what I'm talking about. Okay. So we have a C nu Caratheodory section. C to E. Okay, and then we do this case by case. All right, so I'm trying to reduce the amount of time I spend scratching things on the blackboard. All right, so now we'll look at this case. Okay, so C is locally, integrally, C nu bounded. Okay, And so that's the L1 version. I will also simultaneously give the L infinity version. And I'll call this locally essentially C nu bounded. If, okay, for every compact K, okay, there exists a G okay, so G is positive real value function defined on our integral t, and it's locally L1 integrable. Okay. Such that, okay, and so basically what we do is we ask that the semi-norm of Xi be bounded by G on K. All right, so how that reads is that P, K, M of Xi, T, X, okay, is less than or equal to G of T for T and X, T cross K. Okay, so all of our definitions are basically going to be reproductions of this. So when I write these down, I will be giving kind of abbreviated versions of this. I'll give the complete one here, but so I'm going to omit a lot of this language with the other definitions.
So why do you need to do it case by case?
Just for once to be clear. Yeah. Okay. I mean, you could, Savar's right. You could just put PK nu here and have the other data be, the M and the A for real analytic things. Okay, but I'll do this case by case here, just to make sure I get it right. Okay, or at least I state it clearly once. Okay, so, all right. And so basically I'm just going to reproduce this part of the definition. Okay. All right, so for every compact K, all right, there exists again a G. So, you require here that this be true, okay? And additionally, you have to have the dilatation of this guy is also bounded. Okay, so you need a P, K, M. Okay. Right? All right, so in the smooth case, you're indexed by a K and a non-negative integer M. Okay, so I'm abbreviating, and I even forgot to do it here. All right, so I also mean I forgot it even here. I'm sorry. Sorry. I'm defining two things at once, so I really need to do that. Okay. And then such that. Sorry. Okay, so this is integrally bounded. This is essentially bounded. Okay, so now So I forgot to do it here, but I'll include it here and I'll stop doing it from now on. Okay, so there's the G, which is where it's supposed to be. Okay, so here now it's P infinity, A, M. Oh, sorry. This absolutely actually doesn't make sense. I apologize. Yeah, I'm sorry. I'm sorry. I'm doing this too fast. What I mean is this. Okay, because the semi-norms are applied to sections. Okay, and this is then for every T and T. Sorry. Okay, apologies. Okay, there's a version of that where you evaluate point-wise, but you just use the definitions, of course, of the semi-norms. Okay, so sorry about that.
Your variable P is possibly infinite? Is that right?
Yeah, absolutely. Yeah, but we're only talking about local.
Yeah.
So. Okay. All right. Okay, in the holomorphic case. So now I'll really start abbreviating. So now it's P hol K. Okay, so remember here that this is P holomorphic is really just P0 because you're only talking about basically the C0 compact open topology. All right. Yeah,
just
sure.
The way I see these conditions, that these are precisely the conditions that allow you to differentiate under, basically to pass in zero analytical negligible.
These conditions here for the smooth case?
Maybe in the smooth case, that's right.
Yeah, absolutely. Yeah, when you, that's right. So, exactly. Yeah, that's right. Yeah. In the analytic case? Yeah. Okay, but and here the Lipschitz case includes the Lipschitz constant in the definition, but that'll just be exactly the Caratheodory condition in the existence of uniqueness theorem for ODEs, right? It's exactly the standard existence and uniqueness theorem for ODEs is that this vector field, time-varying vector field, be C-lib integrally bounded. Yeah. Okay, and then finally in the analytic case, you have P omega K A of CT plus to G of T. Okay, so as Saber said, you can really, once you understand that the piece of K notation can be applied to all of these cases, there's really just one definition here, and it's the, P, K, C, T is less or equal to G of T. Okay? But I wanted to, although I messed it up, I wanted to spell this out in all of these cases separately just so we see. Okay? All right, and I want to make it perfectly clear. I think this is one of the really compelling things about this kind of analysis is exactly that all of these cases of regularity can be really subsumed into a single concise statement, and it really emphasizes the importance of the locally convex topologies in these descriptions of time-varying sections and time-varying vector fields. Okay, and moreover, there's a big theorem here. And the theorem is not hard at this point. So first I'll give some notation so I can state the theorem in a concise way. So denote by L, I, gamma, nu. Okay. All right, so these are going to be the locally integrally bounded C nu sections of Tm with time in the interval T. Okay? And then these are the locally, essentially bounded C nu sections. All right? All right, so then the theorem is concisely stated like this. Okay, so the only thing to understand here is what the symbols mean. Okay, so the symbols here make sense. Let's look at the integrally bounded case first. Okay, so you have then mappings from T into the space of C nu vector fields. And so last time I told you how you define the Bachner integral of those. Okay, and that was for finite measure spaces, but we're talking about locally integrable sections. And so local means that you require this to be true for every bounded subinterval. Right? So for every bounded subinterval, these mappings are L1. Okay, so but the integral here is of course the Bachner integral. Okay, so what about bounded? Okay, so there's no integral here in the definition of bounded. The question is, what's the definition of infinity? Okay, so in what sense are these things bounded? So L infinity functions you think of as being essentially bounded. So I've told you that in these infinite dimensional locally convex spaces, there are two generally distinct Bornologies, okay? And the one I mean here is the von Neumann Bornology, all right? So what this means is that for every bounded subinterval of T, there exists a von Neumann bounded subset of this guy, so that the section, these should just be E. Vector fields are special case for us, sorry. And did I use Tm over there as well? I did. Okay. So for every bounded subinterval of the interval T, there is a von Neumann bounded subset of the space of sections, so that for almost every point in that subinterval, you take values in the bounded subset. The usual definition of L infinity, but now the boundedness here is von Neumann bounded. Okay? All right, so the proof of this is actually easy once we get all of this stuff sort of put in place, okay? Here, it just follows directly. And so why is it von Neumann bounded? It's von Neumann bounded because here's the semi-norms. And semi-norms, von Neumann boundedness means boundedness of semi-norms, okay? So this is just virtually immediate from the definition of von Neumann bounded, okay? And here, again, we use the semi-norms to measure the integrability, and what you need here is you need that these spaces, in order for integrability of the function to be equivalent to integrability of the function evaluated on semi-norms, it's sufficient to have completeness and separability, and all of these spaces are complete and separable. Okay? So once you establish all of this machinery, this result is, straightforward, actually. Okay, good. And what time do I have?
10:01.
01, okay. All right, good. So this gives us a nice family, supposedly, of time-varying vector fields. So why is it nice? All right. So it's nice because the flows of these vector fields have nice properties. Okay? All right, so now let's talk a little bit about flows. Okay? All right, so just by standard local existence and uniqueness results, you have existence and uniqueness of flows, except in one case, and that's in the m equals 0 case. All right. So in the m equals 0 case, so for continuous vector fields, okay, so we're going to be working with now a time-varying vector field. Now I do mean Tm. Okay, and so you'll recall that when you have a merely continuous vector field, it doesn't have a flow necessarily. Right? What it lacks is uniqueness. So there's no flow. Right? So we're always going to assume here that nu is at least lip. So what that means. And here m has to be positive. Okay? All right. All right, so the first thing I'll note is something that I've already said a few times. That is the requirement that x being gamma Li gamma lip, okay, is exactly, when you express it in coordinates, the conditions of the Caratheodory existence and uniqueness theorem for time-varying vector fields, or time-varying differential equations. Satisfy, let me say, conditions of okay? So therefore, for all, because with this condition, lip is the lowest degree of regularity. Okay, so all of my vector fields will have local flows. Okay, so what I mean by a local flow is I mean this. So I will probably not get this exactly right. There's too much data for me to store it in my memory. Okay, so what's a flow? A flow is a mapping, phi, I'll write it, from t cross t. Okay, so this will be initial time, final time, initial condition into M, okay? So you choose an initial condition here, initial time here, initial condition here, a final time. So I already messed it up. So So what I mean really is that I have a mapping like this. Okay, and I'll write this as phi x. Okay, so what I actually have is I have a subset of initial conditions, initial times, and final times. Okay, and the flow is defined on that subset of initial conditions, initial times, and final times. Okay. Because, of course, flows generally are not defined globally in time.
Why not just t cross L there?
Initial time and final time, because it's time varying.
Oh.
Yeah. Okay. And so, what are the conditions that define d sub x and phi sub x? Okay. So you know, these things will be uniquely prescribed by some conditions. Okay. And this is what I will not get exactly right. Okay. And I don't really care that much. I have the right conditions written down in our book. All right. So first, for T naught and X naught in M, T cross M. Okay, this set. Okay, so this is for a given initial state and an initial time. This will be the set of possible final times. Okay, well, this is an interval. Okay. All right, and then you have sort of composition formulae like this, and so I'll certainly make a mess of this. Okay, so let's say I start with an initial time s, a final time t, and I apply the flow to an initial time. So the initial time here and the final time here will have to agree. So s, and then tau, and then x. Okay, right. So this is applying flowing from the initial state x at initial time t to final x, so to final time s, and then I do it again from initial time s to final time t, and this is, if I didn't mess it up, that. Okay. All right. All right. So you have some properties of the curves, right? So the integral curves of these vector fields have some properties, and as functions of t. Okay. And that guy is absolutely continuous. So what does absolutely continuous mean here? Because this is now a curve and a manifold, so let me say one way of saying what absolutely continuous means. Okay, the messy way is to say that it's absolutely continuous in coordinates, okay, which is fine. Another way of saying it is that so I'll say a curve, gamma, is absolutely continuous if f composed with gamma. All right, so now this is you hit it with a function f, and so now it becomes a map from R to R is absolutely continuous in the usual sense. Okay, and I'll say that I require this to be true for every smooth function f. In fact, you really only need to check this It's equivalent, in fact, to check this only for, of course, differentiable functions.
Not even C1?
Differentiable functions.
But that's
Oh, sorry, yeah, sorry, continuously differentiable, thank you, yeah, for sure. Okay. All right, and then, all right. So again, this is not an exhaustive list, but it sort of captures the important stuff. And the one thing here that's distinct is this: for every T1 and T naught and T. And X naught in M. So I'm saying this now in a very awkward way, I apologize, such that okay, I meant to just say every T1, T naught, and X naught in D sub X, there exists a neighborhood U X naught such that T1 T naught X is in EX for every X in U. Okay, so all right, so what this means just right off the bat. All right, so this is an initial condition, an initial time, and I know that the flow is defined for a final time T1. Okay, so right off the bat, this is telling me that there's some neighborhood of this initial condition whose flow is also defined for these initial and final times. Okay. And this is, existence of flows is kind of an open condition. That's what this is saying. And that's the big thing here, right? So this map here maps the initial condition, okay, to the final state, starting at T naught and ending at T1. And so it tells you that this map is of class C nu. Okay, and this is true for every nu. Okay, and so this is the thing in the real analytic case. This is a new result. It tells you that this class of vector fields that we're talking about here, this Li, gamma, omega, this class of vector fields is a natural class of vector fields that give you regularity with respect to an initial condition. Okay, so in the all right, so this is sort of classical in the lib case. Okay.
Sorry. So
Yeah.
you have U subscript X0 there, you don't have an
Oh,
subscript.
okay.
Just to know, sorry.
Yeah, thanks. Yeah. Sorry. Where? Sorry. Where? What?
For every X, yeah.
Okay.
So there is a neighborhood X0 and M such that is in the domain for every X in X0.
Yeah. Right. So the flow is defined for with initial condition X. Yeah.
And such that the map from that UX0 to M is class C nu. I see. So around every point.
You can vary the initial condition so that the dependence of the final condition on the initial condition is class C nu. That's C nu dependence on initial conditions.
I see.
That's the way you say that precisely. Yeah. That's right. So that's when you talk about differential equations, you kind of don't really actually think carefully about it in this way. But this is really just C nu dependence on initial conditions. Yeah. Okay. So this is very nice. So let me say something about the proof of this. So in the lib case, this is the classical result, and Rob showed me that in fact, so the classical thing here is really just that in the nu equals lib case, you classically prove that you have continuous dependence on initial conditions. But Rob showed me that it's also that dependence on initial conditions is also Lipschitz. Okay, so it's C nu really. Okay, so that's the standard result, more or less, with a little bit of extra stuff to show that the dependence isn't just continuous but Lipschitz. Most of the time people only care about continuous dependence, so that's all they ever really talk about. Okay, and in the finitely differentiable and smooth case, basically what you do is you prove this by induction. Okay, so you have you basically take your differential equation for the flow of the vector field, and you differentiate it a certain number of times, and then you do it by induction. Okay, in the holomorphic case, the proof goes like this. Remember how you prove it in the normal case. You prove it by Picard-iteration, and so basically you set up a sequence of sort of final conditions. Okay, and then you get convergence. And what's that? In what topology is that convergence taking place? It's taking place in the C0 topology, and holomorphic functions are closed under the C0 topology. All right, so if you start with something holomorphic, you end up with something holomorphic. Okay. Now, in the analytic case, I suspect you can do it this way. You can prove. It's basically your observation about taking derivatives in under. So I think what you can do in the analytic case, although I haven't done this, is you can kind of take semi-norms under the integral and make it work out that way. But I haven't actually done it that way because there's a neater way to do it, and it also contains some other useful information. So I'll tell you what that is right now. Okay, so for Li gamma omega t, in fact this is nothing about vector fields, it's only about sections of vector bundles. We have the following characterization. All right, so the way you check that something is in here, by the definition that I gave, is you involve this sequence of positive numbers converging to 0. Okay, in principle, according to the definition I gave, you have to check that condition for every such sequence. Is that how you want to do it? No, it's not. If you're given a concrete example of a real analytic vector field and you want to check that it's Li gamma omega, you'd like to complexify it, right? And work with the complexification, because the complexification is actually easy to check that it is Li, locally integrable in the sense that I defined. And so basically what we have is a result that says that you can always do that, and it's necessary and sufficient. Okay?
So
yeah.
I think so with ground, when you have the ground embedded here, the holomorphic manifold you embedded in, is it Stein?
It can always be chosen to be Stein.
That's
exactly the key. That's what allows you to do this. Yes, exactly. Yeah. But for this, what we're doing Stein isn't important. Yeah, but it's important for that LF business. That's all. Yeah. Sometimes Stein is essential. Sometimes it's not. For here, it's not. Yeah. Okay. Okay. So for a mapping, C from T cross M into E. Okay, so we're talking about sections of vector bundles here. All right, so the first condition is that C is in Li gamma omega. Okay. All right, and then the next condition is that for every T and X in M, okay, there exists a T prime T and a neighborhood U M of X. Okay. And so I've stopped using proper grammar now. A U bar. Okay, so U bar. Okay, so U is, let me see, so, right, so U bar. Right, so I have a complexification M bar, and I'm saying that there exists a neighborhood U bar of U contained in M bar, so U bar is now a complex neighborhood. Okay, such that, okay, and continuing to use improper grammar, C bar. Okay, so C bar is in L(I) gamma hall of T prime, T U bar. Okay, such that C of Tx is C bar, Tx or Tx in T prime U. Okay, so what it shows you is you can always locally complexify this vector field. So you can always locally complexify the vector field, okay, just by freezing a time and then holomorphically extending the vector field for that fixed time. Okay. The thing that's difficult to show here is that there is a fixed neighborhood U bar. Okay. So in other words, this U bar works for every t. That's the hard part here. Okay. You can do it for a frozen t, but showing that you can do it for every t is really non-trivial. Okay. All right, so this allows you a very concrete way of checking whether you have a vector field that is Li gamma omega, okay, rather than having to verify the semi-norm condition for every sequence of positive numbers converging to 0. And in fact, of course, this is how you would actually do it in real life, right? If you had something which depended analytically on state, and you want to examine its properties as a joint function of state and time, you're going to holomorphically extend, and you want to work with, you're going to replace X with Z, basically. Okay? And so this tells you that that actually works, and it gives you precisely the conditions to describe something here. All right? Okay, so I think I'll stop there for today.